Say we are taking a solid element is under here, and we are saying that it is under coplanar loads like P1, P2, P3 under a same plane as it is given here by shaded portion. Now due to these loads, the stresses will be developed only in the plane itself. So the stresses developed because of these planar loads are called plane stresses. Right? Now if you want to know the stress value, let's say at point O, how we are going to get it? So we take is the plane portion and we cut a section along y-axis and along x-axis through that point. And why this choice of our coordinate axis is dependent upon generally upon the problem itself, what type of problem you are dealing with and for which particular section or coordinate axis will be suitable for that particular problem. Now as we know, the stress is nothing but force per area, so area itself is dependent upon, as we are changing the orientation, so area will change, and that's why stresses also will change. So because of orientation changes, stresses also value will change. Now let's see, if we cut in this section and we are cutting this section, right? Now what we are going to get, now we are taking, let's say we are cutting through this y and y axis. So we see the free body diagram from left hand segment and right hand segment. We are getting these resultant vectors here and here, and if we decompose it, we'll get the normal stress and the shear stress, normal stress and the shear stress, which are same but in different two. It is in this direction, here it is in the alternate reverse direction, because we are taking the same point from this point of view. How? Because of this, how much stresses are here, and in this segment, because of this, how much stresses are in this section. So we are getting normal stress and shear stress because of these different forces are acting. So because of these different forces, there will be a resultant internal resultant stress vector, sigma r sigma r, and we are decomposing it in two directions, one through x-axis, one through y-axis, and we are getting normal stress and the shear stress, sigma and tau. Same way, when we are cutting through x-axis, that is x-axis section, we are getting same way, we are getting different resultant, but we are getting a resultant force. Again, we are decomposing it into direction, we are getting normal stress and shear stress, but these values are different. As this stress is along the y-axis, so it is sigma y, and in this case as it is along x-axis, so it is x sigma x. Similar shear stress, we are here getting tau and tau, here we are getting tau dash tau dash. So as we are changing the orientation, it is along y-axis and this is along x-axis. So as we are changing the orientation of the section, so we are getting two different values, sigma y and tau. So to know the state of stress around O, what we are going to do, we will make a small rectangular element where it is dx and dy, and for this For this direction we are getting sigma x, and in this direction we are getting sigma y, and shear stress we are getting, like, as we are taking this section, like this section, so we are getting from sigma in this direction, sorry, tau in this direction, sigma x in this direction, sigma in x this direction, sigma y, and for this sigma is in this direction, tau is in this direction, so sigma is in this direction, tau is in this direction. So now we are taking this in this way, sigma y in this direction, tau dash in this direction, sigma y, tau dash in this direction, sigma y in this direction, tau this axis, sigma is. So around the, we are getting a complete state of stress at point O. Around it, sigma x, sigma y, and tau and tau dash. Now it can be shown that this tau and tau dash, because it is in the equilibrium, so tau and tau dash will make tau, these two tau will try to rotate this element, but tau dash will try to rotate in this direction. So the whatever couple is forming due to tau, it will be complemented by the tau dash. So it can be shown that the tau and tau dash have the same values. So ultimately we are getting sigma x, sigma y, and tau. So therefore the state of stress in two-dimensional case can be described by only three components: sigma x, sigma y, and tau. The state of plane stress at the point is uniquely represented by two normal stress components, sigma x, sigma y, and one shear stress, that is sigma, which is acting on the element that has a specific orientation at that point. For this particular orientation, we are getting these values. I hope you understand. Thank you.